We are continuing with the textbook exercises. Question number 27. Use the periodic table to answer the following. Identify an element with 5 electrons in the outer subshell. So the elements of in the P block, in case of, in group 17, they have 5 electrons in the P subshell. That is 2P, 5, 3p5, 4p5, 5p5. So all these elements have 5 electrons in this outermost subshell. So any one of these elements will count. Next, identify an element that would tend to lose 2 electrons, that would tend to gain 2 electrons. So elements in the alkali earth metal series, that is beryllium, magnesium, calcium, strontium, barium, and radium, all these elements will tend to lose 2 electrons. Whereas the elements in group 16, that is the chalcogens will tend to gain 2 electrons to reach the inert gas configuration. So any one of these elements can be written as the answer. So we can just write oxygen for the third one, magnesium for the second, and fluorine for the first. Identify the group having a metal, non-metal, liquid, as well as a gas at room temperature. Now, in the in this side of the group periodic table, the elements of group 17 have a metal, that is iodine. Bromine, chlorine, and fluorine are non-metals. Bromine is a liquid, and chlorine and fluorine are gases. Iodine is a solid. So this particular group, that is the halogens, have a metal and non-metals, as well as they also have. So that's halogens here. The 28, the increasing order of reactivity among group 1 elements is lithium, sodium, potassium, rubidium, and cesium. Whereas that among group 17 is fluorine, chlorine, bromine, iodine. Explain. Now, basically, lithium, sodium, potassium, as we go down the group, the reactivity seems to be increasing. Whereas over here, in this case, fluorine, chlorine, bromine, and iodine, the reactivity seems to be decreasing. Question, why? So basically, the main difference between these two is the fact that in our metals, the electrons are lost, which means it is easier for rubidium or cesium or potassium to lose electrons compared to lithium. So the effective nuclear charge, if it is less, it is easy for these elements to lose electrons. And so because of that, lithium has the least reactivity in this group. And so because it again has to do with the atomic radius. Atomic radius increases as we go down the group. Ionization enthalpy will decrease, which means it is easier for these elements to easily lose the electron. And so they have, as we go down the group, the reactivity is increasing. On the other hand, the elements of group 17, fluorine, bromine, and iodine, their reactivity depends upon gaining electrons. So as we go down the group, obviously the ionization enthalpy will decrease, but however, it is easier. So it is easier for chlorine to gain fluorine and chlorine to gain, actually it's easier for chlorine to gain electrons than compared to the other elements of the periodic table, in its group. So because of that, as we go down the group, the reactivity is decreasing. So here it is because the electrons are lost, here because the electron is gained. So it's easier for fluorine and fluorine to accept electrons than compared to bromine and iodine. Question 29, write the general outer electronic configuration of sp, d, and f block elements. So the electronic configurations are given over here. And we discussed about the electronic configuration and their elements and their respective blocks and their characteristics in detail in the previous videos. Assign the position of the element having the outer electronic configuration Ns2, Np4, N3, N equals to 3. So 3s2, 3p4. Generally for P, for our P block elements, 4, right? Now, I find this is the easiest way to understand this. Think about this. Our P block, the group 18, have 6 electrons in their outermost shell. which means this has 2 electrons less. So group 18, 17, and 16. So group 16 will have the electronic configuration of 3s2, 3p4. So and since it has 3 as its outermost shell, it's in the third period. So here, third period, 3s2, 3p4. So basically 18, this will have 6 electrons. This will have 5 electrons, this will have 4 electrons. So you just need to remember that because its outermost p orbital has only 4 electrons, it means that it belongs to group 16. I'm just deducting 2 electrons from our general thing, and then that the same number with respect to the group. The next one, n-1 d2 ns2 for n equals to 4, which means it's in 3d2 4s2. Basically, it'll be 4s2 3d2. So this for d block, in case of d block, you just need to add the number of electrons in this shell. So 2 plus 2, that's equal to 4. So this particular element belongs to group 4. So you'll have 1, 2, 2, 4s2 plus 3d2. So 1, 2 again. So because of that, it will, we're just adding the number of electrons which is present in the s orbital and the d orbital to give us the group number. So had it been 4s2, 3d4, then it would be 4 plus 2, that's equal to 6. So it belongs to chromium, right? So for first of all, for P, we're just deducting, we're figuring out with respect to the number of electrons which are in the P shell. In case of D, we are just totaling up the number of electrons in the D orbital as well as the S orbital. Next, n-2 f7, n-1 d ns2. So here the n equals to 6. So 4 f7, 5d1, 6s2. So if you notice, our 4f orbital is not full, which means electrons are still getting added to the 4f orbital, and all the elements which have this particular configuration will belong to lanthanoids or actinoids. And since it's in the 6, it will belong to lanthanoids, and it is going to have the I'm sorry, it belongs to group 3, this one. The first and the second ionization enthalpies of these certain elements are given to us below. Now we need to figure out their respective characteristics. First of all, the least reactive element. Here, the least reactive element is 5. The reason I say this is because of 2. First of all, its ionization enthalpy, first and second, both of them are very high. Not only that, their electron gain enthalpy have a positive value, which means this particular element is technically an inert gas. So this is the least reactive element. Next, the most reactive metal. Now, the reason, so we will be considering this, and this. The reason we're not going to be considering these 2 elements is because these have a high negative electron gain enthalpy value, which means it should be on the right side of the periodic table. These have a less negative electron gain enthalpy. So 1, 2, and 6 are being considered. Now, the element 2 has the least first ionization enthalpy. Also, it has a low comparative to this and this, it has a lower compared to this, it has a lower negative electron gain enthalpy, which means that this is the most reactive metal because it's easy for this particular element to lose electrons. The next one, the most reactive non-metal. The reason it's 3, now I said this and this is being considered. This is because these have a high negative electron gain enthalpy. So the most reactive non-metal is 3 because the ionization enthalpy of this particular element is higher than this one. And it's more than that, it has a very high negative value for electron gain enthalpy. So 3 is the most reactive non-metal and 4 is the least reactive non-metal. Technically, these are the 2 non-metals which are present over here. Next, the metal which can form a stable binary halide of the formula Mx2. Now, the reason we say that it's element 6 is because it has a very low first ionization enthalpy, but it's higher than that of alkali metals. Okay, and therefore, this is an alkaline earth metal, and it's easy for this particular metal to form an metallic halide. It will form a binary halide. Okay, so basically your ionization enthalpy, the electron gain enthalpy, all of this will help us figure it out. Not only that, there's one important thing I'd like to point out. The reason I say that this might be an alkali metal rather than this one is because of the fact that the first ionization enthalpies are pretty low, but the second ionization enthalpy is quite high. Whereas this, it's not as high as these two. So because of that, these belong to alkali earth metals. Now, I think we discussed about this in the question, in one of the previous questions comparing sodium and magnesium. Sixth one, the metal which can form predominantly a stable covalent halide of the formula Mx. Now, the element 1 has a very low, a low ionization enthalpy, and it has a very high second ionization enthalpy. So this means that it's an alkali metal. And so because of that, it will form predominantly a stable halide, covalent halide with the formula Mx. So in a nutshell, you need to remember that the ionization enthalpy for metals will be less negative. Sorry. I'm so sorry. For metals will be low. For non-metals will be high. First thing. Second thing, the electron gain enthalpy for metals is less negative, whereas the same for non-metals is more negative.